Assalamu alaikum shabab. Inshallah today we'll be talking about the property tables, how to calculate the properties. In this course thermodynamics, or mainly, or in thermodynamics in general, actually we have two main applications. We have the heat engine and the refrigeration system. Heat engine actually which converts the heat into work, like the steam power plant. For electrical power generation, we burn actually fuel to generate some heat. We add this heat actually to water to convert it to steam. Then actually we can expand this steam in a steam turbine. Then we can generate shaft power. We can connect this shaft power, as you know, to an electric generator. Then we can generate electrical power. So we call this actually steam power plant as a heat engine system working on a cycle to convert actually the heat input, convert it into power in this case. And the working fluid in case of a steam turbine actually is the steam. We have water, we convert it actually from the liquid water, actually we convert it to steam under high pressure, high temperature. Then we can generate power in the steam turbine. So that's why actually steam is a very important fluid. And we need to know more actually about the properties of steam and how we can calculate the properties of steam. Also, we have another one major application, or the second major application for thermodynamics, which is actually the refrigeration and air conditioning system. In refrigeration and air conditioning system, they are cooling system actually. In refrigeration system, we are cooling like food compartment, like the fridge or any refrigeration system in supermarket or something. Those refrigeration systems are working actually using freon or refrigerant. This freon actually is a fluid with very low saturation temperature. So when it is passed actually through a system, it can absorb the heat. But on the other hand, actually, it consumes work, electrical power to run actually kind of electric motor. This electric motor run a compressor to compress the freon through the cycle. So the reverse of the heat engine cycle is the refrigeration cycle. Refrigeration cycle absorb work or have work input and convert this work actually into heat transfer or control of heat transfer. And that's why also we have the refrigerant, the freon. In this course, yani, we don't have freons actually have different type and kind. In this course, we are only concerned actually with the properties of one freon, which is a refrigerant called actually refrigerant 134A. We need actually to know how to calculate the properties of this refrigerant under different conditions, also similar to steam, as actually we have wide application of this refrigerant in air conditioning system and refrigeration system. So inshallah today we'll be talking actually how to calculate those properties using the property table. Either for steam, we'll learn how to use a steam table, and actually the same steps can be applied actually to calculate the properties if we have a refrigeration system for the refrigerant 134A. Okay, so today inshallah we'll be talking about the property table, including the steam table and also refrigeration table. We said steam to convert actually to get steam, we have to convert this steam, this water actually from the liquid phase to the vapor phase. And we have looked actually at the phase change process on the temperature specific volume diagram. And we got actually this curve, which is the saturation curve. The top point of this curve actually is the critical point. As we said, above this point, we cannot distinguish between the liquid phase and the vapor phase. But below this point, actually, to the left-hand side of the saturated liquid line, we have actually the zone of subcooled, or we call it actually as compressed liquid zone. The state of the substance in this case actually is subcooled liquid, and actually the temperature is less than the saturation temperature or the boiling temperature. When we reach the boiling temperature, in this case actually when we add more heat, then we have a saturated mixture between the saturated liquid line and saturated vapor line. So in this zone actually we do have saturated mixture. The temperature in this zone, while the phase change is fixed, pressure is equal to B saturation and temperature is equal to B saturation. Temperature is equal to T saturation. And after reaching actually the saturated vapor, if we added heat, then we can reach actually this zone, which is actually called the superheated vapor zone. And in this case, the temperature is greater than the saturation temperature. And we said for each of those zones, inshallah, we'll be having a table. Like talking about actually steam tables. For steam tables, actually, as we said, we have three tables. One table actually for the subcooled. So we have subcooled or compressed liquid table. This table actually is table A7 in the property tables. I have sent to you already the property tables. We have another table actually for the saturated zone. We call it actually the saturated table, or tables in this case, because in the saturation zone we have two tables, table A4 and table A5. Table A4 is similar, actually exactly the same A5. T4 is just starting with temperature, but T5 actually is just actually starting with pressure. So if temperature is given, I will be using table A4. If pressure is given, in this case, I will be using table A5. But they are identically actually the same. Then we have actually the superheated table. We have one superheated table. If the steam actually in the state of superheated steam, then in this case we'll be just using actually table A6. Okay. Now this is regarding actually the steam tables for steam power plant for actually electrical power generation. This is actually the common application for this case. As we said, also we have refrigerant table, refrigeration table. We do have actually different kind of refrigerant. In this course only we have one refrigerant which is called actually 134A. This is the only refrigerant we are concerned about. As we said, the refrigerant has very low saturation temperature. So usually actually it is very hard to actually find this freon in the liquid state. That's why for refrigerant 134A, we don't have subcooled table. We have saturated table, tables. We have table A11 and table also A12. Table A11 is similar to A4. If temperature is given, we can use it. If pressure is given, we can use table A12. And so for the superheated refrigerant, we have to use the superheated table, which is table actually A13. Okay? Inshallah, today we'll be following the steps how to use the steam tables, but actually typically the same steps can be applied if the working fluid is a refrigerant. Then in this case, the same steps can be applied to calculate also the refrigeration table. So in any application, in any problem, I have to look actually, is this problem the working fluid? Is it steam? Then I will be using the steam tables. Is it refrigerant? We do have refrigeration cycle or air conditioning cycles. Then in this case, I will be using the refrigerant table, which is refrigerant 134 or 134A, which is the only refrigerant we are concerned about. In this course. But let's start actually and look at these tables, the different tables, and see actually how we can calculate the properties. Starting first of all, as I said, I will be talking about the steam tables, and then you can apply the same steps if the working fluid actually is refrigerant in this case. Okay. Right, let's start actually for steam with the saturated table. For saturated tables, we have table A4 and we have table A5. We said table A4 is starting with temperature. We can use it if temperature is given. Table A5 is starting with pressure. We can use it actually if the pressure is given. You can look at actually here. This is the table A4. If you look at actually this table, starting with temperature at a given temperature, starting actually from the ice point, which is very close to zero, and then actually for a range of temperature, it gives besides this temperature, it gives actually the saturation pressure, which is the pressure at which we can have phase change at this temperature. It gives you actually the value of this pressure. So in table A4, at a given temperature here, let's say this is the temperature, the saturation temperature at which we have phase change. In this table, it will give you the properties. At this point, we have saturated. The state of the substance is saturated liquid. So all properties have the subscript F. VF, internal energy UF, enthalpy HF, entropy SF. Also here at this point, we have saturated vapor. It will give you the properties of saturated vapor V gas, internal energy U gas, enthalpy H gas, and also entropy S gas. So at a given temperature in table A4, it will give you all the saturated liquid properties V fluid, U fluid, H fluid, S fluid, and also will give you all the saturated vapor properties. So in this case, if you look at the table, specific volume V fluid will be given. This is actually just beside the saturation pressure. You will find V fluid is given. Then he will give you V gas, which is the specific volume of saturated vapor, and he will give you what we call actually VFG. So the parameter, if you have VFG, is the difference, just the difference between V gas and V fluid, which is the difference between a specific volume of saturated vapor minus a specific volume of saturated liquid. And also besides this here, you'll find here, it will be given the internal energy U fluid, internal energy U gas, then beside he will give you UFG similarly. So UFG again, in this table, the value of UFG is the difference between U gas minus U fluid. This internal energy in the table, the unit, as I told you earlier, this is a specific internal energy calculated in kilojoule per kilogram. And this is the specific volume calculated in meter cube per kilogram. Also in this table, he will give you also the enthalpy H fluid, enthalpy H gas, and then he will give you HFG. HFG is the enthalpy, the difference between enthalpy H gas minus H fluid. And also the unit is kilojoule per kilogram. And this HFG is called as actually latent heat of vaporization. Okay? So the difference, HFG, is actually the latent heat of vaporization, the amount of heat required or added to convert the phase from saturated liquid to saturated vapor. So if we have the enthalpy of saturated vapor, if we subtract this enthalpy from saturated liquid, then in this case we can get the amount of heat added actually to convert the phase from the liquid phase to the vapor phase. So this is called as actually latent heat of vaporization, which is HFG. So HFG is defined as actually latent heat of vaporization. Okay. But we have defined, just to recall, enthalpy is equal to internal energy plus the flow energy B multiplied by specific volume. Okay, so the specific enthalpy is equal to specific internal energy plus pressure multiplied by a specific volume. And the latent heat of vaporization HFG is equal to H gas minus H fluid. But look here, Shabab, if we said this table, saturated table, can be used actually if the state of steam is saturated mixture. Okay. But when I go actually to the table at a given temperature, I can get actually the saturation pressure. So this temperature, this line, green line, represents the saturation temperature. And this line gives us actually the line of saturation pressure at this given temperature. Okay. But when I go actually, if we have a steam at saturated mixture at a given temperature in table 4 given for you, then I can go to the table, I can get the properties, saturated liquid properties, and saturated vapor properties. But what if I am here? If it is actually the state is saturated liquid, then we can say at this temperature, so the volume will equal to V fluid, internal energy will equal to U fluid. If the state is saturated vapor, then at this temperature I can go to the table and I can say actually the specific volume will equal to V gas, internal energy will equal to U gas, and so on. But what if we have mixture, not saturated liquid or saturated vapor? Let's say actually I'm at a given state here. As we said, all points between saturated liquid and saturated vapor have the same temperature and have the same pressure. But if I'm in between here at a given point here, how I can calculate the specific volume at this point? When I go to the table at this temperature, I will get V fluid, and also I will get what? V gas. But how I can calculate the specific volume at a given state for a saturated liquid plus vapor mixture? By knowing the values of V fluid and V gas. But let's look here. So the specific volume is defined as actually as the total volume per unit mass. So the total volume divided by the total mass in this case. But let's do this and see how we can relate actually the total volume to the specific volume of saturated liquid and the specific volume of saturated vapor. Okay. So the specific volume is defined as actually the total volume divided by mass total. So V total divided by M total. If we have saturated liquid plus vapor mixture, then we have fluid. So we have the volume of the fluid and the volume of the gas. This is the total volume, and the total mass is mass of fluid plus mass of gas. Let's take this as one term and take this as one term. Then the specific volume will equal to V fluid divided by total mass, mass of fluid plus mass of gas, plus V gas divided by the total mass, which is mass of fluid plus mass of gas. Let's multiply this term first. Multiply this term by mass of gas and divided by mass of gas. So this mass of gas divided by total mass, this term is the quality of the mixture X. We said when we have saturated liquid plus vapor mixture, we can define the quality of the mixture X, which is the mass of vapor divided by the total mass. But what about the total volume of the gas divided by mass of gas? This term represents the specific volume V gas, which is this value, which we can get from the table. So this term is equal to V gas, specific volume V gas multiplied by the quality X. And about this term, multiply actually by mass of fluid and divide by mass of fluid. Okay? And then here, just add mass of gas and subtract the mass of gas. So mass of fluid plus mass of gas divided by total mass, this is 1, minus mass of gas divided by the total mass, this is X, so this term will be 1 minus X. And we have total volume V fluid divided by mass of the fluid, that is the specific volume V fluid. So this term will equal to specific volume V fluid multiplied by 1 minus X. So it will equal to V fluid, specific volume of saturated liquid, multiplied by 1 minus the quality X, plus a specific volume V gas multiplied by the quality of the mixture X. Or we can say the specific volume will equal to V fluid plus X multiplied by V gas minus V fluid, which we call it actually as VFG. And this is the relation by which actually we can calculate the specific volume at a given state here, and actually by knowing the value of V fluid and V gas, and in this case the value of the quality of the mixture should be given in this case. And similarly, actually, we can calculate the other properties. We can say the enthalpy, the internal energy, will equal to U fluid plus X multiplied by UFG. Enthalpy will equal to H fluid plus X multiplied by HFG, and then entropy will equal to S fluid plus X multiplied by SFG. Entropy يا شباب, also in the table you will find all of the properties, specific volume V fluid, V gas, and VFG. Also you will find U fluid, U gas, and UFG. Like this also the enthalpy, and like this also the entropy, S fluid and S gas and SFG. The entropy يا شباب is calculated, is the property calculated in kilojoule per kilogram Kelvin. We said entropy is a measure of randomness of the molecules, or it is actually a measure of the activity of the molecule. It is actually the heat kilojoule applied actually per kilogram of the fluid to have temperature rise 1 Kelvin. But actually this heat or this energy is not allowed to be converted to work. This energy cannot be converted to work. Just this energy is used actually in the kinetic energy of the molecule. So it is actually dissipated in the kinetic energy or the movement of the molecules. So usually if we have high entropy for the molecule, that means actually this system has actually higher energy losses due to actually the random motion of the molecules. And we actually express this property, random motion of the molecules, by, or the activity of the molecule, by this property, which is the entropy, which is in kilojoule per kilogram. We have the third law of thermodynamics, شباب. We have defined the zeroth law of thermodynamics, based on which actually we have the temperature scale. If we have two bodies in thermal equilibrium with a third body, then the two bodies are in thermal equilibrium. Then we have the first law of thermodynamics, which is actually the main subject of this course, and second law of thermodynamics as well. Inshallah, we'll be talking about. Then we have the third law of thermodynamics. Third law of thermodynamics, which actually gives the property entropy is equal to 0 when the reference temperature is equal to 0. So this is called actually the third law of thermodynamics. So the property entropy is very important, and it is a measure actually of the losses within the system. Inshallah, by the end of this course, we will be talking about we'll be talking actually about in this course with the entropy generation. Entropy generation of the system is a measure of the losses within the system. So as we will see in chapter. Why losses? Because actually this entropy gives us indication about the energy consumed in the kinetic motion of the molecules. Okay. Type to be actually in the saturation zone. What will be the condition to be in the saturation zone? The condition in this case in the saturation zone, all point, let's look at this line at given temperature T, all point here from saturated liquid to saturated vapor have the same temperature. We call it actually the saturation or boiling temperature. And the pressure, also they have the same pressure, which is called actually B saturation. Now what about specific volume? Let's first of all define X. The value of X should be greater than or equal to 0 and less than or equal to 1. X is equal to 0 for the saturated liquid, we don't have gas. X is equal to 1 when we have saturated vapor, we don't have liquid in this case. And in between X should be greater than 0 and less than 1. Then what about the specific volume? If we are in the saturation zone, the specific volume should be greater than V fluid and less than what? Less than V gas. So V is greater than V fluid or equal to V fluid or less than or equal to V gas. If it is equal to V fluid, then the state is saturated liquid. If it is equal to V gas, the state is saturated vapor. In between, so in this case we have saturated mixture of liquid plus vapor. Similarly, we can say for the internal energy, U fluid and less than U gas and sub B will equal to greater than H fluid and less than H gas, and the entropy is greater than or equal to S fluid and less than or equal to S gas. And these are the conditions to be in the saturation zone. So the conditions to be in the saturated zone. So if we have steam under this condition, any of this condition, that means the state of this steam actually is saturated mixture in this case. Okay, and we can use actually in this case table A4. A4, if the temperature is given, it gives actually at a given temperature, it gives the saturation pressure in kilopascal. Table A5 is the same. If pressure is given, then in this case I can use table A5. It will give you the saturation pressure, and then actually the same properties, V fluid, V gas, VFG, and also like other properties, internal energy, enthalpy, and so on. What about actually this is what we said. I'll solve inshallah examples after I finish talk about how to use the table. What about actually, this is the saturated table. We have two other tables. We have superheated table, and also we have the subcooled table. Okay. For the superheated table, we are talking about steam. For superheated table, then in this case we will be just using table A6. If you look at table A6 actually is a combination actually of a series actually of sub-table. At each of this table, the pressure value will be given, and actually for a range of temperature, starting actually from a given temperature and go on. Then in this case, the value of the specific volume will be given, the value of internal energy will be given, the value of enthalpy, and also the value of entropy. Then in this case, if you have the pressure, I will just select the table of this pressure value, and then actually at a given temperature, then we can go to the table and read the values of a specific volume, internal energy, enthalpy, and entropy. In this case, actually in the superheated zone here, in this case, we don't have V fluid or V gas. This is actually for the saturation zone because we have fluid and we have gas. But in case of superheated zone, only we have single phase, which is the gas phase. So we don't have V fluid in this case or V gas, just we have V in this case. Okay, so to be actually in the superheated zone, in this case actually the pressure and temperature will be given. I will select actually which of those tables. You can look here actually at table. This is table A7, this is table A6. Table A6 here, you can see starting with pressure value equal to 0.01 megapascal. This is the pressure value, and for a range of temperature actually starting from 50 it gives the value of a specific volume, internal energy, enthalpy, and the entropy. And here also another table for another pressure value and so on. So at a given pressure, I will just select a table from those tables and look at the given temperature. Then we can read actually the properties of the volume and other properties, internal energy, enthalpy, and the entropy. Type the condition actually to be in the superheated zone. In this case, we have to check first of all the state of steam, either it is subcooled, saturated, or superheated steam. So in this case, we set to be in the saturation zone. The properties V should be greater than V fluid and less than V gas. But what about if the specific volume is greater than V gas? That means actually the state of steam is what? Is superheated steam in this case. So the conditions to be in the superheated zone, conditions to be in the superheated zone. In this case, actually, as we said, in the superheated zone, the temperature should be greater than the saturation temperature at a given pressure. Okay, so in this case, actually, let's say actually at this pressure value, at this temperature, this is actually the line of saturation pressure as we have presented here. Okay, but at this pressure value, in this case, to be actually in the this is T saturation. To be actually on this line at a given pressure, any point here to be in the subcooled region, any point has temperature that is less than the temperature T saturation. This is actually for the subcooled region. But for the superheated region, to be actually in the superheated region at this given pressure, any point here actually has temperature that is greater than actually the saturation temperature at given pressure. Or we can say actually, like what we said last time, the pressure in the superheated zone is less than the saturation pressure at a given temperature. But look here at a given temperature. This is actually the given temperature. Given temperature. This line represents actually a line of temperature. For this line to be actually on this line at any point actually in the subcooled region, any point here has pressure that is greater than what? The saturation pressure at this temperature. And on this line actually to be in the superheated zone, any point here has pressure that is what? This pressure is less than the saturation pressure. This is the line of saturation pressure. Okay? So in the subcooled region, the pressure is greater than B saturation at a given temperature. For this given temperature, for any point here, the pressure should be higher than the saturation pressure. But at this temperature, at any point here, the pressure here at any point is less than what? Less than the saturation pressure. So to be in the superheated zone, the pressure should be less than the saturation pressure at a given temperature. If the temperature is given, we can go to table A4. Then in this case, I will get the saturation pressure and compare with the given pressure. If the given pressure is less than this P saturation at this temperature, that means the state is superheated steam. And as we said, if the volume is greater than V fluid and less than V gas, the state is saturated. But if volume is greater than V gas, that means the state is what? The state is superheated in this case. Okay? So if a specific volume is greater than V gas, that means actually in this case the state is superheated steam. So V is greater than V gas, or like this actually the internal energy U is greater than U gas, enthalpy is greater than H gas, and the entropy is greater than S gas in this case. And this is actually the condition. Those are the conditions to be in the superheated zone. Sorry, شباب يعني the property table was just hiding the board. I will just repeat this one quickly to just let you understand about how the pressure is less than B saturation to be in the superheated zone and greater than B saturation to be in the subcooled region. This is actually the temperature specific volume diagram here actually. So let's say at a given temperature, so this actually T saturation. This line should represent actually the saturation pressure at this temperature T. Okay. طيب at a given temperature T, at this line temperature, To be actually on this temperature in the subcooled region, any point here has pressure. This is the line of pressure. This pressure greater than B saturation. So to be in the subcooled region, the pressure should be what? At any point at a given temperature should be greater than B saturation. But here at this given temperature, to be in the superheated zone, any point here should have pressure. This is the line of pressure. This pressure is less than what? Less than B saturation. This is the saturation pressure at this given temperature. So any point here will have pressure that is less than B saturation. And this is the condition to be in the superheated zone. Pressure should be less than B saturation at a given temperature. But the temperature is greater than T saturation at a given pressure. So at a given pressure here, let's look at this pressure line. Any point here has a temperature that is less than what? T saturation at this given pressure. And at a point here, any point here at this given pressure should have a temperature that is greater than T saturation. And this is actually the condition to be in the superheated zone. For the subcooled table, if you will, I will just, for subcooled table, similarly actually, it is very similar to the superheated table. Or for the subcooled table, I will be just using actually table A7. It is exactly the same as table A6. Table A7 also has a given value of pressure, and for a range of temperature will give you all the properties. And the condition actually to be in the subcooled region, the condition actually for the fluid to be in the subcooled region, this at a given temperature here, as we said, this is V fluid, and this is actually V gas. To be between V fluid and V gas, this is saturated. If the specific volume is greater than V gas, then the state is superheated. And if the specific volume is less than V fluid, then in this case the state is subcooled in this case. And in this case, the conditions to be in the subcooled region, first of all, we said, what about temperature? In the subcooled region, temperature is less than the saturation temperature at a given pressure. And as we said, what about the pressure? Pressure should be greater than the saturation pressure at a given temperature. Unlike this, we can say the specific volume should be less than V fluid, internal energy less than U fluid, enthalpy less than H fluid, and also the entropy is less than S fluid. And those are the conditions to be in the subcooled region. Okay, but let's see what we are going to do. In this case, our target actually is to calculate the properties. And we said to specify a state of a substance, we have to define two independent and intensive properties. Okay, two independent and intensive properties. We said for steam, in case of saturated mixture, we said all point between saturated liquid and saturated vapor, any point here in between actually have the same pressure, same temperature. So in this case, we cannot say pressure and temperature are independent in case of saturated mixture, because actually all point has the same pressure and same temperature. We cannot make difference in this case. And for this region, the value of the quality X should be given in this case. Okay. So our target actually is to calculate the properties, given actually two independent and intensive properties. So let's see actually a summary how to use actually the steam table. And same steps can be applied for the refrigeration table. So what are the given option in this case? So option number A, actually, it will be given for you either pressure or temperature plus one of the specific properties, like a specific volume or a specific actually internal energy or a specific enthalpy or a specific entropy in this case. So it will be given for you two properties, either pressure with one specific property, let's say pressure and a specific volume are given. Then we can take those two values and calculate all of the other properties using a steam table. Or it can be given temperature with a specific volume, then we can go to the table to calculate the properties. Or pressure with any property, pressure with internal energy, pressure with enthalpy. Any two independent and intensive properties, we can go to the table and calculate the properties. Now let's say here pressure or temperature is given with one of those specific properties, either V or A or U or H or S. Okay? Then in this case, if first of all actually we have two options in this case. Either we can go to actually table if the pressure is given. So first of all, if the pressure is given, we can just take this pressure and go to actually table A5, or actually in this case, if the temperature is given, I will be using table O4. So in this case, I will take this pressure or temperature. I will be using to table A4. Table A4 if T is given. So if the temperature is given, I will be using table A4. Or I will be using actually table A5. This actually in case if pressure is given. Okay? But in this case, either table A4 or A5, if pressure or temperature is given. Then in this case, let's say actually we are given, the specific volume is given with either pressure or the temperature in this case. So I will go to table A4 if T is given, or A5 if pressure is given. Then I will get actually the property V fluid, and also, which is a saturated liquid specific volume, and also I will get V gas. But let's say pressure is given with the internal energy. Then in this case, I will get U fluid, and also I will get the value of U gas at this given pressure. If the temperature is given, go to table A4 and get actually the same properties. Similarly, we can get actually the other properties. Let's say if H is given, then I will get H fluid and H gas. And we have two options in this case. So first of all, I will compare actually those values to the given value. So if we find the given specific volume is greater than V fluid and less than V gas, then in this case actually the state of steam is saturated mixture. And as it is saturated mixture, so that means the temperature is equal to the saturation temperature. The given temperature is equal to saturation temperature, and also the pressure is equal to B saturation. And in this case, the next step actually is to calculate the quality of the mixture X. Okay, but we have defined, let's say V is given. So V is equal to V fluid plus X multiplied by VFG. Then in this case, V is given, V fluid and V gas actually, and VFG we can get from the table at the given pressure or temperature. Then we can calculate the quality of the mixture X will equal to V minus V fluid divided by VFG in this case. Now I have calculated X. Then I can calculate actually the other properties. Internal energy will equal to U fluid plus X UFG. We can get U fluid and UFG from the table by the given temperature or the given pressure. And like this, we can say enthalpy will equal to U fluid plus X multiplied by HFG. Entropy will equal to S fluid plus X multiplied by SFG. And by this, actually, we can calculate all the other properties. So let's say temperature is given and a specific volume. With this temperature, I will go to table A4, get V fluid and V gas. And we are given a specific volume. Compare with the given specific volume. If I found the given specific volume is greater than V fluid and less than V gas, that means we are in the saturation zone. So the state is saturated liquid and vapor mixture. At this zone, actually, the temperature is equal to the saturation temperature, which is the given temperature. And from table A4, we can get, besides this temperature value, we can find the pressure value, which is the V saturation in this case. Then we have to calculate the value of X using the given specific volume and the values of V fluid and VFG, which we can get from the table. Then we can calculate the value of X. To calculate the other properties, we can calculate for internal energy, we can get from the table at the given temperature, U fluid and UFG. Then we can calculate using this equation and the value of the calculated X. We can calculate the internal energy in kilojoule per kilogram. Unlike this, we can calculate the enthalpy and the entropy in this case. Type, this is option 1 under actually the mean given pressure or temperature with one of the specific properties. Type, what about if we find this specific volume is greater than V gas in this case? Right. This is step number 2. In this case, if we found actually the given specific volume is greater than V gas, V is greater than V gas. That means we are in the superheated zone. So the state of the steam is superheated actually steam. And in this case, for the superheated steam, in this case, I have to use table A6. Okay? Given in this case pressure, and I can define which pressure table I will be using in this case. And for a range of temperature, you can find V, U, H, and S. I will specify the pressure table, then go actually under a specific volume. A specific volume is given. Then in this case, once I get the value, I can read actually the other properties. Temperature, internal energy, enthalpy, and entropy. All of the properties can be confirmed. Internal energy, enthalpy. Also, we can get the entropy. And if we need to calculate, if temperature is needed, then we can get actually the temperature in this case. Okay? So this is actually the second option. The third case actually, if we find actually the given specific volume is less than the fluid, that means actually the state in this case of steam is subcooled. And subcooled, in this case, we have to use table A7, similarly to the case of A6. Then we can calculate the other property, U, H, S, and the other properties using the given actually, the given pressure and the given value of specific volume. This is actually the main case when pressure or temperature with one of the specific properties is given. Let's say if we have pressure and temperature are given. If pressure and temperature are given, so as we said, pressure and temperature are not independent in case of saturated mixture. So if pressure and temperature are given, that means the case cannot be actually saturated mixture because pressure and temperature are not independent. All point has the same pressure and temperature. We cannot calculate the properties in this zone for saturated mixture using pressure and temperature. So in this case, if pressure and temperature are given, that means the case should be either subcooled or superheated. So option B, so will be given pressure and temperature in this case. So we have in this case also two options. Either we can take actually this pressure, and this option actually I prefer, and then I will be going to table A5. Table A5 at the given pressure, we can get from this table actually the saturation temperature. The value of saturation temperature we can get it. Then we can compare actually this saturation temperature with the given temperature. And we have here 1A, option 1A, if the temperature is less than the saturation temperature. The saturation at this pressure, I will take it, go to table A5, get the saturation temperature. From table A5, you will find here actually the pressure is given, and beside pressure, the saturation temperature is given. So at this pressure, I can get the value of saturation temperature. Compare this saturation temperature with the given temperature. If the given temperature is less than T saturation, T is less than the saturation temperature, so that means actually the state in this case is subcooled liquid. Subcooled liquid, that means we have to use what? We have to use table A7 to calculate actually the properties. We can calculate the internal energy, specific volume, enthalpy, entropy, and all the other properties in this case, given the pressure and the temperature in this case. Type option 1B, if we find actually this temperature is greater than the saturation temperature, temperature is higher than the saturation, that means the state actually of steam is superheated steam. And in this case, I have to use table A6 in this case. Okay? Table A6 to calculate the other properties like specific volume, internal energy, enthalpy, and entropy in this case. But this is option number 1. To take the pressure and temperature is given, then I will take this pressure, get T saturation, and compare this T saturation with the given temperature. If it is less than T saturation, that means subcooled, I will be using table A7. If it is actually greater than saturation, so it is superheated, then I have to use actually table A6. So first of all, Shabab, we have to check. I'm giving two properties. He didn't say actually either it is subcooled, saturated, or superheated. So in this case, for any case, we have to check first. Check using the saturation table. Either I will be using table A5 if pressure is given, table A4 if temperature is given. But in this case, pressure and temperature are given. So I will take either pressure, go to table A5, get the saturation temperature, and compare with the given temperature. Or we can take this temperature and go to table A4, get the saturation pressure, and compare the saturation pressure with the given pressure. Usually I prefer, if pressure and temperature are given, to take the pressure to get the saturation temperature, because you keep it in mind very well that if the temperature is less than T saturation, then it is subcooled. If it is higher, then it is superheated. But the reverse in case of pressure. But I will write it down as well. So if pressure and temperature are given, either to take pressure and go to table A5, or in this case, actually, you can take the temperature is the same and go to table actually A4. So the second option is to take this temperature and go to table A4. In this case, I will get actually from table A4 the saturation pressure. So in table A4, you will find the temperature, and besides the temperature will be the saturation pressure. And then compare case of 2A, if actually this pressure, given pressure, is greater than the saturation pressure. Pressure, if it is greater than saturation, that means the state is subcooled. So in this case, it is subcooled. And in this case, we have to use actually table A7 to calculate the properties VUHS. Type 2B, if we find actually the given pressure is less than the saturation pressure, pressure is less than B saturation, that means the state actually is superheated steam, and in this case we have to use table A6 to calculate the properties VUHS, all of these properties. Okay? So either given pressure or temperature with one specific property, then we can follow the step A. Then, or actually, if pressure and temperature are given, we said they are not independent in case of saturated zone. Then, if pressure and temperature are given, the state will be either subcooled or superheated in this case. Okay. So let's have a third option, which is very important also. It's a kind of a special case. So if pressure and temperature are given, so case C, so it is given pressure and temperature, and I have made all of these checks, and I found actually that the state is subcooled. So I am confirmed that the state is subcooled. I compared actually get B saturation or T saturation and compare with the given temperature. So I checked, I found the temperature is less than T saturation, so the state is subcooled. But when I go to the subcooled table, when I went to the subcooled table, searching about actually the required pressure table, I didn't find this value of pressure. So in this case, if you look at actually this saturation table, table A7, if you look at table A7, you will find this table A7 is starting with pressure value equal to 5 megapascal. Okay. So the subcooled table is starting with pressure value is equal to 5 megapascal. If the pressure actually given pressure, let's say 2 megapascal or 1 megapascal, then in this case we don't have table. Like what should we do in this case? Let's look here. So look at the process on the TV diagram. This is the saturation curve. We are given actually a point here. This point actually on the TV diagram has a temperature. This is the line of temperature at this point. And in this case actually, this is the line of pressure at this point. This is the line of pressure. And at this point actually, at this temperature, this is the pressure B saturation at this given temperature. So B saturation at the given temperature T. Okay? And this is the temperature T. So we are at this point. If I need to calculate the specific volume, this is actually the specific volume that I need to calculate. But we don't have table, so I cannot get this value. But we have saturated table. If at this given temperature, if I went to the saturation table, table A4, I can get the value, this value which is V fluid. But this is V fluid at the given temperature, which is from table A4. Okay? But at the given pressure, this is actually the pressure, the given pressure line. If I went to table A5, this value here will be V fluid, the value of V fluid, but at a given pressure, which we can get actually from table A5. Okay? So which of those two values, Shabab, is close to the actual value? The value V fluid at a given temperature is the closest value to the actual value. Then in this case, we can take this assumption. In this case, if the state pressure and temperature are given, the state is subcooled, but value
is not listed in table A7. Value is not there. Also the case يا شباب in case of refrigerant 134A, we don't have even subcooled table. So if we have refrigerant and the state is subcooled, we don't have the whole table. Not only the pressure value, we don't have the whole table is not existing. So in this case, we can assume V will equal to V fluid at the given temperature. This is actually should be calculated from which table? From table A4. At the given temperature, go to table A4, we can assume actually V is equal to V fluid. Unlike this, actually internal energy is equal to U fluid at the given temperature, enthalpy will equal to H fluid at the given temperature, entropy will equal to S fluid at the given temperature in this case. Okay? Usually in the subcooled region for the liquid, their properties are not affected much with pressure. Here, for actually in the subcooled region, if we have 100 times increase in pressure, that will result in only 1% change of the properties, unlike the case of temperature. So in case of subcooled or compressed liquid, the properties actually can affect by temperature much more than the case of pressure. Okay, and that's why we can take this valid assumption. But what about enthalpy? Enthalpy by definition is U plus BV. That means enthalpy is mainly function of pressure. We can take this assumption, it's okay, it can go. But if you want to calculate more accurate value, we can say enthalpy will equal to H fluid at the given temperature, which is this value, plus a specific volume at the given temperature from table A4, multiplied by the pressure difference, which is B, the given pressure, minus B saturation at the given temperature. B sat at the given temperature, which is this value. B sat at the given temperature from table A4 at the given temperature, you can get B saturation. And this actually pressure is the given pressure, and this is V fluid at the given temperature from table A4. Like this in enthalpy H fluid, then we can calculate. This is actually more accurate value of enthalpy. But you can take this assumption anyway. Okay? But this is actually, Shabab, what I want to say. Just last thing about the table, which I have to mention here, is the interpolation. So let's say in a table, let's say given pressure and temperature. Okay? Given a temperature value here, I need to calculate, let's say, the specific volume. The temperature here in the table is 100, 200, 300, and so on. But if I need to calculate the specific volume at a temperature, let's say, equal to 150. This value is not listed in the table, just we have at 100 and 200. Okay? So let's say at temperature 100, we have a specific volume V1. At 200, we have specific volume V2. Let's say this 100 is T1 and this 200 is T2. And that temperature T in between, I need to calculate actually the value of a specific volume V. Then we can make interpolation. Interpolation in this case. We can just say T minus T1, the temperature I need to calculate at it, which is 150 minus T1, which is 100, divided by T2 minus T1, which is 200 minus 1. That will equal to the specific volume I need to calculate, minus V1, which is listed in the table in front of 100, divided by V2 minus V1. Okay. So this actually interpolation can be done in this case if the value is not just lying in between actually two values within the table. Okay, this can be also, instead of interpolation, can be extrapolation. If I need actually to calculate a value outside here, outside 100 and 200. Also the same, we can say T minus T1 divided by T2 minus T1 equal to V minus V1 divided by V2 minus V1. So either interpolation or extrapolation. Okay, so thank you, Shabab, for this. It was tough class, but we have to go with.